All right. Chapter number 4, creating and applying capture filters. There is a difference between capture filters and display filters. Display filters don't limit the number of saved packets. They can be used with existing trace files and live captures. All right. Chapter number 4. Oh, I forgot to mute myself. There we go. All traffic is recorded for later use, so you don't have to worry about did you miss a conversation in the background. Display filters will help you zoom in on the conversation at hand, but it doesn't take out any other conversations that are happening. In comparison, capture filters will limit what is being saved, because capture filters are looking at what is coming into Wireshark and taking out everything that doesn't meet that filter. They can't be added to existing trace files. They can only be added when you're going to capture. And when the capture filters are applied, all other traffic is discarded and not recorded. So capture filters are great if we're trying to hone in on a specific machine, for example, and ignore other machines on the network. We just want to focus on one and its communication. Whereas display filters, if we want to see everything that's happening on the network and filter later, those come in handy then. So because capture filters are very specific in what is being brought up into Wireshark, it's not possible to revert the rest of the traffic after it's applied. Filtering by protocol is one of the basic ways to use a capture filter. You could do host and then define the host. That could be to or from the specified device by IP address. You could do destination, and that is traffic to a specified host. You could do ether host, and that's by MAC address. You could do net and say to or from a specific IP address that starts with whatever you decide. You could also do the network and the subnet. So your filter, your basic capture filter is pretty versatile. Then we have the primitives. These are commands that don't need arguments for Wireshark to understand what you're asking. For example, TCP, UDP, IP, ARP, IPM6, IP6, it understands these. You can do incoming connection attempts, whether they're successful or not. For example, like this with TCP and then whatever flag you want and TCP-SYN does not equal 0. You can do exclusions. If you don't want traffic or a certain device traffic saved, then you could use not ether host or not ether host and then the MAC address. You could do by applications using ports. So you could do port and then whatever, or TCP port, whatever, or source port, whatever. You can use operators like not or the exclamation point, concatenation using the and or the ampersand, alteration or the pipe. You can make your own capture filters as well to add to this list that you can you can use later when you're running a new capture search. From the main page, you'll click on capture and then capture filters. You can make one and call it My Mac, for example. And you can make one that is everything except your Mac. As a test run, you can make a filter that captures all TCP packets between port 70 and 90. And you could see with using the My Mac capture filter, it'll only capture your MAC address, anything that comes in and out of your MAC address, and the not my MAC will capture everybody else except your own. Colorizing traffic is awesome. It'll help you in differentiating the many different conversations that are happening on a network. Wireshark does have a default coloring rule, but just like with everything about Wireshark, you can modify it. For example, you could go into View, Colorize Packet List. Color rules are applied in order from top to bottom, so keep that in mind if you're adding a rule. If you want it to take effect above all others, then it needs to be at the top of the list. Laura Chappell talks about using but ugly coloring rules, which I think is a great idea. If you want certain traffic to stand out, use a but ugly color. Use something that's really going to stick out so that when you see it, you know this kind of traffic is happening. For example, if there is a brute force happening and you have you understand that we're working with an FTP server and you want Wireshark to highlight for you anytime somebody's trying to enter a password, you use a but ugly color, it'll stick out like a sore thumb immediately when somebody's trying to log in and repeatedly try to log in. Again, color conversations to distinguish them. You can right-click any one of the packets, and then you could temporarily mark the packet of interest as well. That could be with Control-M. Shift-Control-N will find the next marked packet. Shift-Control-B will take you to the previous marked packet. You can alter the stream reassembly coloring as well by using any one of these, following UDP, TCP, or SSL streams. And you can go to Edit Preferences, User Interface Colors. Here is an example rule that you can set. Opening ESPN 2001.pcapng, find the 301, have a coloring for anything for any HTTP response errors that are above 399, and then you'll see any errors, for example, packet 9, in a different file, HTTP 500 error, you'll see packet 9 light up with whatever color you chose. Again, making it easy to find these errors, easier to look at the traffic and figure out what's happening. In a different file, you can open VoIP extension, right-click packet 2. You can select a default temporary color. It's easy to reset by going to View and then reset coloring 1 through 10 afterwards. But again, being able to take a conversation and temporarily color it because you want to follow it, because you want to see what conversation is happening. Piece of cake in Wireshark. Display filters. They, again, enable you to focus on specific packets based on the criteria that you are defining. You can just type them in the display filter box. It has autocomplete, so you don't have to know the whole thing to begin with. You can apply many of the saved filters. You can use all kinds of expressions on it. You can also use the right-click and apply conversation or endpoint filters as needed. Here are some basic filter examples similar to the capture. Display filters can be created based on packet characteristics. It doesn't even have to be a actual field. So for example, you could do the TCP analysis flags, or you could also use operators as well. The crazy thing is you can get really complicated with these. and have filters do all kinds of stuff for you. Like I said, Wireshark has an autocomplete function. For example, if you type TCP and then dot, you'll get a number of possibilities, and you just have to pick the one you're looking for. It can also save display filters, useful when you want to come back later. So here we're saving a display filter on our list. So next time we can just click on it and come back. If you're ever stuck with what filter expression do I need, there is a expression button that has all the possibilities. And if you click on it, you'll see that there is quite the range. Don't forget that right-clicking is always an option. You can always create or apply filters just by right-clicking. Here are some notes. A not selected will create an exclusion filter based on that selection. And selected must match existing filter and the selection. Or selected will be either the existing filter or the selection. And not selected must match the existing filter and not the selection. And or not must match either existing filter or not selection. Your display filter syntax, every field in the packet details pane can be used to create a filter. Whether the field actually exists in a packet or it's one that's a characteristic made by Wireshark, it can be turned off in a filter, or it can be turned into a filter. Just look at the bottom. For example, here, it's telling you what you would use as a display filter. Here are a bunch of ways that you can continue to use comparison operators in display filters. All of these work. You can combine them in all kinds of complex and fun ways. And they will all do a great job. For example, all of these, where we're getting even more complicated. This one will do cookies. So here's a weird one. What the heck does this mean? This means look for MAC address at byte 5, because remember we count from 0, and look for 2-byte value that starts with 221B. Here's another one. IP 14.2 equals 96.2C. Look at the 15th and 16th byte for a source address of 96.2C. Going even deeper, we can filter by specific bytes, like this. Ethernet source address field, look for the 2-byte value that starts with that. The 15th and 16th byte, looking for 96.2C, or the IP address that ends in 150.44. That's another way of framing it. The value of 14.2 means we can count over 15 bytes, starting at 0, and look for a 2-byte value. We can also filter by keywords in upper or lowercase. It has that capability. We can do regular expression within Wireshark. You know, like searching HTTP packets that have a slash dot. That question mark I is case insensitive. And then anything inside that could be like, if we're looking for an exe or we're looking for a zip. This one is email addresses. Here's another one. This will search HTTP for anything that's connecting in a string other than .com. You can go to regexlib.com/tsheet to find out more about the regular expressions that you can use. Some common display filter mistakes tends to happen with the not operand. So we have this. Cool. We're looking for IP address of 10.2.4.1. If you go this way, putting the not equal, that's not the way to say view all packets except the ones that contain that IP address. If you do that, it does mean you are looking for packets that have IP address field containing the value other than 10.2.4.1. The right way that we would use this filter is this, but the not at the very beginning. Or something like this. Now an introduction into graphs. We can use graphs to view all kinds of trends, unidirectional and bidirectional. Here we'll look at the basic I/O graphs, the advanced, the round trip time, the TCP throughput, and the time sequence. Generating basic ones are great for overall traffic in either a unsaved or a saved trace file. The basic thing that it tells you are the bytes seen, including data and headers, but you can make adjustments to this, as you'll see. The way to get there is under statistics, there's I/O graph. The default x-axis is always set to 1 second, and y-axis is set to packets per tick. Of course, you can click on a point in the graph and jump to the first packet used in the range to calculate. So this isn't just a chart that you can't interact with. You can actually click anywhere on the line, and it'll in Wireshark it'll take you to that packet where the line was graphed. So you can generate something like this, for example, by using that file, the TCP upload problem large file. The filter graph is totally based on display filters. So anything that you can use a display filter for, you can graph. There are a couple colors that you can use for your graphs. And there are also ways to differentiate the styles and layers from lines to dotted to the F bars. Here's another challenge. Open up TCP bad download again and see if by adding TCP analysis flags, you can recreate this chart so you can see the traffic visually. Again, Wireshark automatically defines the X and Y axis. X being time per pixel, can be changed. The Y has 4 main units. You can set a logarithmic to identify relationships between 2 plotted points better. Sometimes it's better to use the logarithmic, sometimes not so much. You can smooth, defining moving average between plotted data. You can graph and save as a PNG file. But interestingly enough, it won't save the X and Y. So you might want to take a screenshot instead. Very weird. Your advanced IO graph is in the same place, just under the y-axis dropdown. You can do all these things. For example, the sum, the minimum, the average, the max, count frames, and load. Using sec client dyn, here are two things that you would need to start. And you notice in the y-axis, we've already defined the sum y field. So this will plot the amount of TCP data in the trace file from source to destination. The result will be that graph. The min, average, and max, those are great to graph latency times. Count frames or fields are great for finding specific characteristics, like, for example, analysis flags. Load is good to use to see the client load on a server. I suggest reading pages 501 through 505 for more information. Laura goes deeper into these things, and better than I could honestly put it. So if you take HTTP download good and you graph out the TCP sequence number, what do you notice? There's a weird drop here, and then it goes back up. You can compare traffic trends using the graphs. You can bring in two files and compare them together. For example, in order to do it, you'd first examine the time difference between them. You'd need to alter the time if necessary so that they're the same, and then merge them, and then open the merge trace file and see the generation. See the graph that comes out after merging two together. For example, you can merge HTTP download good and download bad by, for example, using merge cap to bring the two together into a file called merge.pcap. And then when you open up the graph, you'll see this. You'll see the difference between download good and download bad. You can graph the round trip time. Under statistics, stream graph, round trip time graph. They graph the round time based on the corresponding acknowledgements. The y-axis is the highest round trip latency time, and that's calculated as time between TCP data and its acknowledgement. These graphs are unidirectional. So if you see nothing when you open it up, you might be looking in the opposite direction. You might need to flip it. And there's an option to say which way is it going. Consistent vertical line stripes are seen when packet loss occurs and a high number of duplicate acknowledgements are set. This is not good. So your vertical stripes can also mean that data is getting queued along a path. So we have, at some point, there is some device that is buffering data and then letting it through. Those lines are not good. That means we have to go hunting through the network to find what device is not passing data enough quickly that we're getting these duplicate acknowledgements and data is being put on hold. Download good versus download bad. You can create the two graphs to compare and see, is there a problem in the good side? And if so, where? Another question is using the advanced IO graphs, add this into it and see what happens. See if you are able to answer this question. You can graph throughput rates under statistics, TCP stream graph, throughput. So you'll see any trends related to traffic flow. This graph is also unidirectional. So again, if you see nothing, it's probably because you're looking at it the wrong way. So open up HTTP download bad. And here's two questions. What is the throughput rate for the trace file? And do you see when the problem occurred? You can see the TCP sequence numbers over time, which is important to see that traffic is being, the packets are going up in number as they're transmitting data. It'll help you visualize the TCP-based traffic. Again, ideally, the graph plot should run from the lower left to upper right, because as data is being transmitted successfully, the two machines are moving up in the sequence number. Again, the graphs are unidirectional. If you see an I bar, the taller the bar, the more data is being passed. If the two lines ever meet, then that means the window size reached 0, and that means one of the two machines has run out of buffer space, and it cannot transmit until RAM is cleared. So you can use the window scaling graph to see some issues. You can, by using the window size, you can plot the calculated size value sent in each packet. It is unidirectional, but at least you can see who of the two, is it the sender or the receiver who's running out of room in their RAM, which means the application, either the application is slow or the computer is being overloaded, or there's another device along the path who is slowing down the transmission of traffic. So if you open up download video and check out window scaling, what do you see? Again, if you are upstream from a packet loss, you might see duplicate I bars. If you are downstream from a packet loss, you'll see gaps in the I bar. Duplicate acknowledgements are noted as numerous ticks along the receiving line. A high number means there's a high path latency. When retransmissions are triggered, they are not preceded by duplicate ACKS. Awesome.